That's the best thing to do right now. What was the hypothesis of Green's theorem again? There's this curve, a simple curve, right? Simply closed curve, and there's no singularity inside that region. But if it has a singularity, then we're going to do the following. This is a little demonstration, and can be a little bit confusing from now on, but this is a very representative example. So I'm going to erase that orientation. Now, situation is that we have this things around, and inside here, inside there, these vector field is not defined. Okay, so we can only do that in here. You have to remove that singularity with the exaggerated. Maybe it's actually one point, isolated singularity. It's like that. So this is not simply a connected region, right? But we're going to call that region D. We're still going to call that boundary like this, and still positively oriented. Interesting thing is that this region D have several boundaries. You see the outermost boundary in there? Outermost boundary. They're positively oriented. What does that mean? When you go around, the region is to your left, right? So it's going out like this. Is that right? That's how the outside loop is going to be parameterized. Now think about this. This is also a boundary of this region. Boundary is not just an outside, is where the region ends. That's where the boundary is, right? So do you recognize this as a boundary of the region too? Inside loop? So which way does it go around if the region have to be to your left? Clockwise or counterclockwise do I have to go around so that your region is on your left? It must be this direction, right? So that the region is on your left. And this region is on your left. Does that make sense? Okay. So that when we say this multiply connected region with this positively oriented region, was this part of the reading in the section? All right. So I'm going to name this one C1 positively oriented, right? And this one C2 is negatively oriented, and C3 is negatively oriented, right? But that's the name. C1 positively oriented, and C2 negatively oriented, C3 negatively oriented. But that's what that D is. The boundary D is going to be C1 and C2 and C3. Union of all these things, correct? Those are the boundary. But instead of union, we're going to use this addition symbol, if that's okay. The reason we're using this addition symbol, because we're going to use this loop for the line integral, right? So the way this line integral behaves for this union is a sum. So we decided to use this notation. Does that make sense? Okay. Okay. So here's a theorem. If you have this situation, not simply connected region, what's going to happen if you do this vector line integral like that? So again, this boundary of D is one positively oriented curve, one negatively oriented curve relative to inside. It's kind of funny. But C2 is a positively oriented to the region D. This is the statement. That's the same. The region D, which is this with the hole, so curl F is the same. The Green's theorem still holds when the boundary gets more complicated like this. Make sense? So that's the end of the Green's theorem. I'm going to give you an interpretation of this thing. This line integral, let me just abbreviate it like this because inside the vector field is going to be the same all the time. This is the same as this C1 is a counterclockwise orientation, and plus C2 is a clockwise orientation, and C3 is clockwise orientation. And I'm going to look at the situation the curl is a 0. Because we're going to consider function that's complex analytic, then those u and v satisfy nice curl equation. Remember that was a part of the homework, right? Yeah. So u and v gives you a nice curl equals 0 Cauchy-Riemann equation. So that's the situation we're going to be looking at. So if the curl is 0, what's going to happen to this integral, line integral? If the curl is 0, if this theorem is true, the curl is 0 if through the Green's theorem, not, but I think he's trying to go through the point of fundamental theorem of line integral. If the Green's theorem point of view, if the curl equals 0, that becomes 0 there, right? Therefore, entire thing is 0. Correct? So that kind of gives you the path independence, but it's not quite path independence. It's like multiple loops are involved. But this is if this is correct, and this is a statement. Is that right? Now I can separate this one. C1 plus C2 plus C3. Does this notation make sense? Yeah. And then I'm going to isolate C1, and then C1 here is equal to negative C1, C2, negative C3. And inside is all same f dot dr. And I'm going to use this negative to reorient to C2. So let me show you that. C1. So how do you reorient to C2? If it is negative, if I put negative C2 as a backward orientation. Is that okay? If you orientate backward, you simply change the sign of the integral. And if I write a plus, that's a backward orientation. I'm going to go back and draw the picture again. So these generalized Green's theorem allow you to make this connection between these two different loops. And here's the conclusion from that. If you have the curve C1 out there, and I'm going to call that, this one right now is a clockwise rotation, right? But it's a negative C2 would be counterclockwise rotation. Is that right? So I'm going to call that one C2 prime. Is that right? And this one will be, originally C3 is a counterclockwise rotation, but backward is a clockwise rotation. I mean, I said it backward, but I'm going to call that one C3 prime. Namely, it's the opposite direction. All right? So what this Green's theorem says is the following. If you go around C1 and is going to be equal to C2 prime, which is counterclockwise rotation plus counterclockwise rotation. Under what condition? Provided if the vector field, the curl of the vector field is 0, then Green's theorem allows you to rewrite the integral around the C1 as a sum of C2 and the C3. Okay? This is an example. I have this vector field. So what do you know about this vector field from the homework? Curl 0. That's the only thing we have. Curl 0. So I'm going to explain the meaning of this Green's theorem version 2 that we just went through. So here is a singularity 0, 0. That vector field is not defined there, right? And I'm going to give you some crazy curve like this. Suppose I cooked up some trigonometric functions as curve like this. So I'm going to call that one C1. Okay? Then I'm going to draw C2. I'm going to use C2 prime. So I'm going to do C2 prime in red. So here's, this is some crazy curve I give you, and I ask you to do that. It's compute C1 FDR. Okay? Then it really has a crazy formula. You don't have gradient vector field that works for this curve because it goes all around. Remember, this one is the one that is gradient vector field is not defined on this entire horizontal line. So if you go around like this, you can't apply that. And next thing we did was very simple curve. What was that? It's a circle, right? So we can calculate directly. Now, this curve is not just in the first quadrant. It's just go around this thing, and it is not simple. So the thing that we did in the homework doesn't work, and that's where this Green's theorem works in here. So this looks like a hard problem now, right? So Green's theorem says, all right, here's a solution. Starts like this. Right, I know that little one inside, remember that little circle? That was easy to calculate. Why was that? Because x squared plus y squared becomes 1 and it becomes simple, right? So I'm going to call that one. Is this incorrectly parameterized? This is going to be parameterized like this. Is that right? I'm going to call that C2 prime. Just like in the Green's theorem. It was in the Green's theorem, it's clockwise rotation. Now I take it back. What does Green's theorem say? It say to going around like this is the same as just going around inside. If you have a two singularity, you go around like this. You can imagine that if you have only one loop, and it's going to be that one loop. So by Green's theorem, version 2, this vector line integral of a vector field of FDR is equal to, let's see, here the C1 is outside, right? Counterclockwise rotation is the same as counterclockwise rotation, the sum of the counterclockwise rotation of inside. That's what that says, right? As long as it's analytic in here. So let's see. I have this loop around, this crazy loop. Inside there's a loop. Do you think this function f is defined everywhere in between those two curves? F is defined on the shaded region. Is that correct? So that Green's theorem part 2 applies. As long as you can integrate over this region, Green's theorem 2 allows you to do that, even though it's not simply connected. So anybody like to go for the next version? It's this crazy line integral is supposed to be equal to what? Let's go around the C1 it's equal to the inside, whatever you put it in there, as long as it's defined, and as long as the curl is 0, right? Its curl is 0, so that's inside the C2. Okay, so we originally have this like path independence property, right? But right now, something like that is happening. If you go around the C1, and in between C1 and C2, there's no obstacle. There's no undefined pointer in there. You can kind of contract that C1 down to C2, right? Without hitting any singularity. And if your curl is 0, that's part of the condition, then integrating around C1 is same as integrating around C2 prime, counterclockwise. So I gave you crazy formula. You don't have to worry about the crazy formula. You can use the simple formula around that 0, 0. It's going to be the same. Okay? So if I give you this crazy formula and ask you to compute, and then you say, I'm going to actually go around the very simple formula, and the answer is going to be the same. Provided that what? Analytic inside and curl 0. It should be analytic in between those two curves, and curl is 0, and this crazy integral becomes a simple integrals. Make sense? Yeah. So what was the answer? What's the answer to this crazy integral of this wiggly loop? 2 pi. Doesn't matter how you go around, it's going to be 2 pi. All right. So let me give you also this thing. How about this thing going around like this, and there is still 0, 0 in there. And if this one goes like this, right? This one goes like that, goes like that. Well, isn't that just, you can separate that loop, right? What happened, this completely simply connected, right? What happened if you go around in simply connected region over curl 0? Integral for that part is, was a 0, right? It's only problem when you go around that undefined but the loop. If it's just like a first quadrant problem, we're all in the first quadrant problem, and then it's simply connected. Curl 0 means gradient vector field. Gradient vector field is 0 in all simply closed curve, right? All closed curve. So that's a 0, that's a 0, that's a 0, correct? So integral of that tiny loop is going to be all 0. So the integral value is going to be the same as missing that loop thing, right? Correct? So that's the same thing. So you reparameterize it, lose that, and reparameterize it, and therefore it's the same as tiny loop by the theorem that we just went through. Okay? Yeah. But can you imagine that if I go around 2 times, around the 0, 0, right, you go around like this, it started here, and then that goes inside and coming outside like that. So you can separate into 2 curves. Seems like we're dealing with one curve like that. What about the other one? Is that also counterclockwise rotation? So, right? So it's like that. So you can separate it. Doesn't matter how, weird the shape is, this integral is the same as little integral inside. This integral value of that one is still the same. Whatever inside you put around there is always what value? 2 pi. And plus, you're doing it again inside that loop, right? So whatever little thing you put around, you can experiment. Not only the unit circle, any arbitrary small circle you put around 0, 0, you go through the definition, you will find it as still 2 pi. So that's also 2 pi, right? So what is the answer to the integral around this thing? 4 pi. Okay? As long as 2 is there. And how about 0, 0 is there? I go around, but like that. Does this another loop inside really contributes to that integral? If you just isolate in here, inside there's no 0, 0. Therefore, the integral around that tiny loop is going to be just 0. Right? So this is the same as to go around without that loop inside. Okay? So what do you think this integral is really measuring? Once around, 2 pi. Twice around, 4 pi. Right? If you have some crazy curve that's sitting inside some space-time in 4-dimensional or string theory or whatever the dimensional is, if you want to figure out the geometry, how many times you're going around the spinning part, and you actually integrate this one, if the value turned out to be integer multiple of 2 pi, that multiple tells you how many times you go around it. It's pretty amazing phenomenon. You capture that topology into this